All right, we'll get started. Okay, so at the end of last class, we were just going over the assignment. I had to do it like pretty fast because we were out of time, so I'll go through it again, and now that you've looked at it for a week, you might have more questions about it. Okay, so I didn't go through all the red tape of it, but so the assignments you'll do individually, you won't do it with partners or groups. Project you can, but the two assignments will both be done individual. If you use any external material, you can cite it. You probably won't. Maybe you'll use the course notes or something like that. But anyways, if you do use something, cite it. If you can't make the deadline, so it'll be due next week after class at 8 p.m. If you can't make the deadline, you have what I call a slip day. And you can use the slip day. You don't have to ask me to use it or anything like that. You can just hand it in late, basically, okay? The slip day allows you to hand it in 2 days later. So instead of it due Wednesday, it will be due Friday at 8 p.m. If you hand assignment 1 in on time, then you might as well use your slip day for assignment 2. And if you use your slip day for assignment 1, then you can't use it for assignment 2. Okay, so the slip day is for you to use either on assignment 1 or assignment 2, your choice. And like I say, you don't have to tell me that you're doing it or anything like that. We'll see that it comes in late, and then we'll just mark that you use your slip day for assignment 1, and then we'll make sure that you don't use it for assignment 2. Other than that, there's nothing to it. Okay. Now, if there's some reason that you have to hand it in late, like a medical emergency or a family funeral or something like that, like whatever the case may be, then you can have extensions as well. And in that case, you have to come in and email me, okay? But anyways, okay, so that just gives you some flexibility in terms of when you can hand things in. The assignment will be submitted on Moodle itself. So your interface will look a little different than mine as a professor, but there should be like some sort of submit button. You'll just submit it as a PDF. The TA will mark it, so I won't mark the assignments. We have a marker. She'll mark it. You'll get your grade back through Moodle at some point. It takes a while to mark these because, it's a lot of writing that has to get read. Please typeset your thing, upload it as a PDF. Don't handwrite it. One exception would be like if you really want to do a table, you might find it easier to like handwrite it rather than to draw it. But you don't even have to do a table because you're not doing the complete table anyway. You're just doing a row, so you can just do it as bullet points anyway. So probably wouldn't be a big thing. It's easier for us if you put your student number.pdf when you name it, and then you'll upload it to Moodle. So this link will give you the description of the assignment, and it should also give you an interface for uploading it as well. Okay, any questions about the logistics? It's all clear? Okay, so the main thing is the slip day. You can use it for A1 or A2, your choice. You don't have to tell me. You can just do it. And if you do hand A1 in on time, you might as well use your slip day for A2. Okay, so last time we did go a little bit through the premise of the assignment. So it has to do with different ways that you might implement a ticketing system for a concert. Physical tickets is sort of based on paper, and whoever holds the paper, gets admitted. But there's some sort of anti-counterfeiting on the paper. So you couldn't just like create a ticket that looks the same as another ticket. E-ticketing system is like by email, so you have a QR code. This is more or less what most venues would use today. And then the online system takes an additional step of tying the seat to an actual name, and then you would show ID as well as your ticket. In fact, you maybe arguably wouldn't have to show your ticket, but anyways, you can read through the process. Now, these things are kind of sparse, the descriptions, and so when you analyze it, you're going to want to know exactly how it works in detail, so you can make assumptions that sort of fill in those details. Okay, so it might not write down everything explicitly, but you can make reasonable assumptions and just state what those assumptions are. Okay, and then what do you actually have to do? So in the first part of the assignment, you'll look at stride. And so what I want is every 6 categories of stride, I want you to say, starting with the physical ticket system. So you'll start with this one, and you'll give me 3 sentences about spoofing in the physical ticket system. And the sentences should tell me, is spoofing a concern? You might say, oh, there's no spoofing attacks here, right? That has nothing to do with tickets. Or you might say, yeah, there's these kinds of spoofing attacks. Is the system doing anything to stop those attacks? Okay? And so you might say, well, yeah, it does this or that or whatever. And then if you basically, do you think it's enough? Do you think the system is doing enough to combat spoofing? So like I decided there were some attacks, spoofing attacks. I decided these were the mitigations. What's your assessment? Like, are the mitigations good enough, or should they do more? That's more or less what that last sentence is about. Okay? And then what you can do is you can move to the other 2 systems, e-ticket and online, and you can tell me, does the picture change when we move to e-ticketing, or is it just sort of the same? So whether it changes or is the same will depend on the property. And so you can just tell me, yeah, for these 2 systems. Okay? So the whole thing should be like 4 or 5 sentences long, more like 5 sentences maybe. Try and limit yourself. If you do 6 instead of 5, you're not going to lose marks. But if you write 10 sentences, then you might. And you'll go through all the 6 categories of stride. Okay, is that clear? Yeah.
When evaluating certain properties, can
Yeah.
you make some reasonable assumptions about the system
Yeah.
that go a little bit further from what is being described about the system?
Yeah. So you will probably have to make some assumptions anyways. Yeah. And so you can make the assumptions, you can state your assumptions as you need them. So if you need them, because for spoofing, you know, it didn't really say, like, I don't know, like it says it's printed on special paper. Well, like I assume that means that I can't create a copy of it or whatever. Like, and so like whatever your assumption is, then you could state it there and then say why it has to do with spoofing. Yeah. Okay, and all these like restrictions of like sentence about this is all just because if people write free form stuff, then the TA has to mark. You know, everyone's assignment ends up being 10 pages and there's 100 of you and it's 1,000 pages. So we're not trying to restrict you or stop you from clearly explaining your ideas. As long as you're reasonable, it's okay. But at the same time, I just don't want to give the TA like huge essays to read because it's hard to mark. Okay, then we'll switch to evaluation frameworks. And so basically what you'll do is you'll come up with some columns. Okay, so I want 6 from the security category. I want 6 from usability and 6 from deployability. You can look at the difference, like you can ask yourself to come up with columns like, is there any usability differences between these 3 systems? And then try and capture that difference in a column. That's like one way that you might come up with it. The criteria that you come up with, the columns that you come up with, have nothing to do with the columns that we came up with in class for password systems. Okay, because this is, so you're not supposed to use the same columns. You're supposed to come up with columns that have to do with concert tickets. That said, you might decide that some of them are the same, right? Like, is it vulnerable to physical theft? That might be something that's applicable in this scenario that was also applicable to passwords. So you are free to use, and there's a bunch of other evaluation frameworks in these links about other kinds of systems. And so if you see a column that you really like, you can use it, and you think it's applicable to ticket systems, you can use it and just give a citation to where it's from. But what I am looking for are columns that are specifically designed for this ticketing system. You're not trying to go out of your way to use columns from elsewhere. Okay, so just come up with them on your own. And then for every column, you should say, what does it mean to get a full dot? What does it mean to not get a dot? If you want a half dot, that's fine. What does it mean to get a half dot? And just like very clearly state what all 3 of them mean. Okay, and then once you have your columns and you have what it means to get a full dot or a half dot or a no dot, then now you can evaluate the systems. And just to cut down on the amount of marking, you'll do your evaluation only on the online system. Okay, so if you think of it as a chart where there's 3 rows and you have your 18 columns, you're just doing 1 row of it. You could do the other 2. You should be prepared to do the other 2, like the columns are developed and refined and defined in order for you to do it. But just to cut down on the amount of work that you have to do and the amount of work that the TA has to do in marking it, that's why we're restricting you to 1 column, or sorry, to 1 row. So you just have to apply that one, your columns to that one system and say whether for each column you're giving that particular system a full dot, a half dot, or no dot, a sentence of justification, or up to 3 sentences, I guess, where you say why exactly it's a full dot and not an empty dot. Okay, that's all I was going to say about it. Is there questions? Okay, is it a hard assignment? Is it something that takes a long time? Is it easy? I'd say it's like, it'll be a little hard to come up with the columns. That's probably where you're going to find the hardest. You probably will breeze through the security columns. I mean, Stride already has 6. And by the way, you can, all the things, the attacks that you came up with in question 1, you can kind of turn them into columns, like it resists this attack in column 2. So like doing question 1 will help you do question 2. And so you should have 0 problem coming up with 6 security. But deployability and usability, you might find like it's easy to do 2 or 3, and then the last 3, it gets a little hard. So that's probably where you would spend your time, if I had to guess. And then, yeah. And so it is an assignment where you want to sit and think about it. It's better to like try and do it across a couple days. Like come up with a bunch of columns and then give yourself like do other stuff and then come back to it and think about, and maybe like new columns will occur to you like once you take your mind off it. If you just try and sit down and do it from start to finish, probably wouldn't be so good. Yeah, so that's it. Your mark, you'll get back through Moodle. It's out of some weird number that's not 100. And so when you get a mark back like 84, don't think that you got 84 out of 100. You probably got 84 out of 84 or something like that. So anyways, I think now Moodle like reflects your mark as a percentage anyways. But I know in past years people freaked out because they thought they did a really good job, and then it turned out that their mark wasn't out of 100. They were just assuming that it was out of 100, but it was actually out of some number that was close enough to 100, but not exactly 100. Okay, questions? All right, good. Okay, so good luck with it. I'll be here next, you're cutting it pretty close if you have questions next week in class, but technically it's still before the deadline. And I guess if you're slipping on assignment 1, you would still have a couple days after next lecture, so I can answer more questions then. Also, office hours, send me an email, whatever. Ask me after class during the break. Okay, so today we're going to move on to another topic. So we're going to look at a third high-level evaluation, methodology called attack trees. And I'm going to give you a specific example of an attack tree, which is based on this thing called HTTPS. Okay, so we've seen 3, or this will be the third high-level methodology. Evaluation frameworks, you use it when you have multiple solutions and you're comparing them. Stride, you tend to be looking at one particular thing, like what are all the attacks on this one particular system. And with attack trees, you also are looking at all the possible attacks on something, but usually you go even narrower than just what are all the attacks on HTTPS. You'll go narrower to that and you'll say you actually start with a goal of an adversary and then you figure out what are all the ways that the adversary could accomplish that goal. And so if you have one system that you're doing the security analysis of it, you might realize that the adversary has multiple goals, right? They might want to break this aspect of the system or this aspect or this aspect. And if there's 3 of them, then you would do 3 attack trees. So attack tree is meant to be just one kind of attack on one system. We're going to think about every way of possibly doing it. Okay, so it's meant to, it's again, because it's a high-level methodology, it's very, very general. It's like kind of obvious when you look at it. It's not like complicated, but the complexity comes from actually being able to fill out the tree itself. But the idea is to get you to enumerate all the different ways you could attack a system. Okay? Attacks can take one of 2 forms. So sometimes we actually reserve the word attack for like a security incident that actually happened. Okay, that's an attack. And if I'm like, well, theoretically you could do this, but no one's ever done it yet, we might say that that's a threat as opposed to an attack. Okay, so attacks are like something that actually happened, and a threat is something that could potentially happen, but we don't know for sure whether it's happened yet, or we know that it hasn't happened, but it could in theory. Here for attack trees, we're interested in attacks and threats. We're not going to distinguish between the two. Some people actually call them threat trees as opposed to attack trees, but the more common saying, or the way of describing it would be to call it an attack tree. Okay, so we accept both attacks and threats in the tree. And to come up with the things, the attacks that you're going to put into the tree, you can use Stride to think about like what are the spoofing attacks, what are the tampering attacks, et cetera, et cetera. And like any high-level methodology, like Stride, like evaluation frameworks, like attack trees, attack trees will be another example of it. You can't really do it unless if you understand the system that you're analyzing. So we're going to do an attack tree for this thing called HTTPS. I'm not going to assume you even know what HTTPS is or how it works. And you wouldn't be able to do the attack tree until you came to understand how it works. Okay? So part of the lecture is actually, we'll spend a lot of time just teaching you the different properties and how it works in order to then think about what the attacks are, and then in order to actually do the deliverable of an attack tree. Okay, so why is it a tree? So far, it just sounds like a list of attacks, so that's fine. So you can think of it just as, for now, as a list of attacks. But we are going to organize it into what we're calling a tree. And so the idea of the tree is that some attacks are related to each other. Okay, so you'll start with what the adversary's goal is. So the adversary's goal is to break this property of this system. That's going to be like the root node. And then all the attacks, that you won't just have like the node and then 10 attacks that come off of that node. Usually what you'll do is you'll sort of sub-organize them. Like the adversary might take this high-level approach to breaking this property. And then within that high-level approach, there's 3 or 4 like specific ways of doing that particular approach. Okay? And so they would be like leaves of the tree. This will make sense in 2 minutes. We'll do an example and it will make more sense. But anyways, so you have a root of the tree, which is the adversary's goal. You'll have all these paths that sort of branch and fork. And at the very end of a path is a leaf, and the leaf will be the actual attack. Okay, so when you get to an attack, then you stop. And so that will be the leaf. And then if 2 leaves are close to each other in the tree, it just means that they're kind of variations of the same attack. And if they're like in completely different parts of the tree, then they're sort of like completely different attacks. And if you want to understand the attack, it's good to start at the root and kind of walk along the tree, and it will kind of tell you the story of the attack as you move along it. Okay, so we'll move into an example, and these details will become clearer, and I'll go through these properties again so that you can see that they all match what we're actually doing. Just a tip before we go: when we do this process, a way, I'll try and illustrate it with the example that we use. A way that's helpful is you just say, you ask yourself, like, why can't the adversary just do their goal? Like, they have this goal, they want to break the system in this way. Why can't they just do it? Like, what's stopping them? And so there'll be some defense, there'll be some mitigation or some sort of thing that stops them from doing it. And then you'll make your new goal to defeat that mechanism. So you say, the adversary wants to do this, they can't do this because of this mechanism, so now I'm going to try and break that mechanism. And then you think, well, why can't I break that mechanism? Well, I can't break it because there's this other thing. And then my goal is now to break that other thing. And eventually, you might find a path where you can break all the mitigations and find a path to attack the system. So we'll see. I'll try and illustrate this with the example that I'll use. Okay, so the example that we'll do is, let's say I park somewhere in a parking lot and I don't want to pay. Okay, I just want to leave, and it's at Concordia, it's very expensive. It's like $25 a day. I'm in Faubourg here in the parking lot. I want to get out, and I prefer not to pay the $25. Okay, that's my goal. Okay, so in an attack tree, what we're going to do is we're going to think of what are all the ways that you could actually get out of a parking lot without paying? Okay? And what we're going to do is we're going to put them into this sort of tree format, but you don't have to worry about the tree format right away. Okay? So we can start with the root node. So the root node will be to leave the parking lot without paying. And then picking up on that tip, right? The tip is like, well, why can't I just leave without paying? Right? Like what actually stops me? And then once you think through what stops you, then we can think about, well, is that actually always going to stop me, right? And then we can go sort of back and forth. So let's sort of go through the exercise together. So I want to leave the parking lot. I don't want to pay. Why can't I? First off, why can't I just leave? Can I just leave? No? Why? Okay. So it's in the picture. All right. So there's this arm. Okay, great. Okay, so we have an attack. I want to leave. There's this arm. That's the defense mechanism. Now the question is, okay, can I defeat that arm somehow?
Yes.
How?
You can bring other car from other side, from the entry side. When that car will come, it's supposed to open the gate, and that time you can just take out your car.
Okay. So if the input gate and the output gate are shared, then maybe a car coming in would lift it, and then a car coming out could. What if they're different? What if there's one input gate that you can only go in, and the output gate is?
You go to the input gate. If you have access to that,
Yeah.
you just go to the input gate, which is already.
Just which? Oh. Okay. So one thing you could do is tailgate. So you could, if you see another car leaving, right? Cars are different sizes, right? And some cars are trucks, and some cars have trailers, right? And so this sensor, it's going to open it, and as long as there's some weight there or it comes very quickly, it's, two cars going through the gate at the same time look kind of like a car and a trailer going through, okay? So you wait for someone else to leave, and then you follow really closely behind. Great. So that's an attack, okay? So we can put that into the attack tree. So the node of the tree would be, I want to get out of the parking thing without leaving. The thing that's stopping me is this like parking arm, and I'm going to defeat the arm by tailgating someone else, okay? Is that the only way to get out? So pat yourself on the back, you found one attack, okay? But the attack tree, the actual idea of it is to think about all the attacks as well, okay? So is there anything else that you could possibly do? Okay, you could just drive through it. Sure, that's fine. Okay, if there's a wall or something, you can drive through the wall. Say it louder. Okay. So why does the arm not go up when you pull up to it? Okay, it doesn't pull up because you haven't paid, right? Well, what if you were able to somehow do something about the payment system? Okay, so this is now a different branch of the attack tree. So there's the attacks that are directly on the arm itself, and then there's the attacks on the system that tells the arm to open. So if I can fake the payment, the arm works correctly. It's going up. It thinks that you paid, and it's going up. So I didn't attack the arm. I just attack the thing that gets the arm to move, if that makes sense. Okay? So yeah, so I could attack the payment. I could use fake currency. I could look at the ticket and maybe it has like a barcode. And when you pay it, like write something else on top of the barcode. And if I could reverse engineer that, I might be able to like write the barcode that says I paid even though I didn't pay. There's usually some sort of kiosk or terminal. I'm going to walk up to that and pay. Maybe I can breach that. It's a computer. You know, there's all sorts of different things. Okay, so I would call that like, that would be kind of like spoofing attacks, right? If I just drive through the thing, right, that's sort of an extreme version of a tampering attack, but it's sort of like tampering. If I tailgate, I don't know what I would call that, probably escalation of privilege, because the first car is privileged to go out, and I'm just kind of going along for the ride. What about denial of service? Is there any denial of service attacks that you could think of? Okay, so how does that help, though?
DOS is on the system which opens the gate.
Okay, so you could do a DOS on the system that opens the gate. What's something that the system that opens the gate needs that sometimes doesn't always have? Electricity? Okay, so let's say you knock the hydro out. Okay, what's going to happen? No one can leave the parking lot, right? Not usually. What will happen is they'll just open the gate and leave it open, and they know that they're losing money, but what else? They can't keep you there, right? Yeah, so any kind of emergency like situation, fire alarm, hydro outage, all these are like sort of exceptional circumstances, and in exceptional circumstances, it might stay open, okay? Now we have some first off, we're going to see this theme throughout the course. Okay, that exceptional circumstances, like things change, so that this isn't the last time we see it. Another concept that we'll see is we call this a failure. Okay, when the hydro goes out, that's a failure or a failure mode. And we have a permission system, and we have to decide that when the system fails, do we open up permissions or do we close permission? Okay, so in this case, the power failed. We call it fail open, meaning that we remove all the permissions. Okay, so everyone can go in and out without paying. Okay, some systems are configured that way, so they fail open. They try the best they can, and if there's a failure, then they just say, well, we tried, it's not working, so just go ahead and do the thing that you want to do. And other systems fail close. Okay, fail close means that you can't do what you want to do, you can't do the check, so you're just going to say, well, you're not allowed to do it until the system comes back. Okay. From a security perspective, fail close is always more secure than fail open. Okay. But from a practical, like living your real life, right? Sometimes you need fail open systems because people aren't going to tolerate being locked into a parking garage for a couple hours because the power went down. Okay. So this is like where the real world and your ideals about what should be secure sometimes have conflicts. So we'll see other examples of failed open, failed close types of things. Okay, anything else that people can think of?
If you can, suppose there is a guard sitting at the gate.
Yep.
He can manually just control and open the gate. You can just talk out with the guard and he can just open the gate just for you.
Okay. So instead of attacking the gate, we're again going to attack the mechanism that opens the gate. Payments would get the gate open, but there's usually a manual override as well. Like when the power goes out, someone has to open the gate, right? And so there's a security guard. The security guard has a key, right? So you could do any number of things. You could tell them a story about why you need to get out without paying. Yeah, you can do some violence, threaten some violence. You could, this actually happened to me inadvertently. So there were times where I left a parking lot without paying. One time I just folded the ticket in my pocket and it had like a magnetic barcode and then it wouldn't scan. So I just told the guy, it's not scanning, and they were just like, okay, fine, just go, right? And usually these types of things, you can do it once, right? But if you go every single day and you always have your folded ticket and you try and get out every single day, it's not going to work, kind of thing, okay? But anyways, you could try and steal the key itself, okay? You take a picture of the key. If you can get a picture of a key, imagine like a security guard and the keys like on a keychain on the belt of the security guard walking around. You get a picture of it, then you go to a 3D printer, you print out a key that's a perfect replica, and then you can open it yourself. Okay? So anyway, so that also would be an attack. Other ideas that people have. I think we did pretty good, but
Put a stopper on the arm to make it permanently open.
okay, so we could do some tampering with the arm itself to stop it from closing. That would be another thing.
If you have really look like example, can you try for the bar?
Okay, so maybe the bar itself wouldn't work, right? So maybe you could evade it without damaging it as opposed to driving through. So yeah, if you have a sports car that's really low to the ground, maybe you could get under it. Maybe you could just drive around it. You know, it depends. Like here you can see there's these like curbs and all of this kind of stuff, but like maybe there's some way to just drive around it. What else? Okay, here's a question. What happens, here's my idea. I have a brilliant idea. Tell me if this works or not. Let's say you go into a parking lot and it's full. What happens? Okay, you'll go to another parking lot, but do I have, let me make it very specific. Do I have to pay if I go into a parking lot, I drive around for 3 minutes realizing that all the spots are taken, and then I leave right away? Usually not, right? Usually you don't pay unless if you're there 5 minutes or 30 minutes or something like that. Okay, so here's my idea. I go in the morning, I park, I go about my day, and in the evening I want to drive home. So I've been there 12 hours, I'm going to pay $25. But on my way into the parking lot, I just walk up to the in machine. I press the button to get a new ticket, right? And then I go to my car and I drive out and I put the new ticket in, and it thinks that I've been there for 2 minutes.
Could be.
Sounds good, right? Okay. There's one problem though. Actually, it won't work.
Because when you take out the ticket, there should be weight on the sensor.
Yeah, that's exactly right. Yeah, so most parking lots anyway would have some sort of weight sensor on the in. So if you went to the ticket and if you went to the machine and pressed the button, it wouldn't spit a ticket out because it wouldn't think there's a car sitting there. So that's why they stopped that particular attack. Okay, so attack, I want to do this like get a fresh ticket. Defense mechanism is now the weight sensor. So we moved away from the whole parking system just to the weight sensor. Is there now an attack that we could do on the weight sensor? If we can attack the weight sensor, then we can get the new ticket. And if we can get the new ticket, then we can get out. You have any friends?
Yeah.
How many people would have to stand on the weight ticket? You know, depends on your friends, but you know, probably 10 people, right? You could all stand there and press the button and it would think a car is there, okay? Or another thing you could do is, this is a more sophisticated attack that actually is a variant of ways that people attack voting systems. If you had a friend who was coming in around the time that you were leaving, then you could swap tickets. So they could give you their new ticket. You could get out for free. Now they're stuck without a ticket, right? But when they go to leave, hopefully another person's coming in, and then they could do that swap. And so you could keep doing this swap. As long as there's new people coming in as old people are going out, the new person can give the new ticket to the other person. And eventually at the very end, it's kind of like a chain. The last person will be stuck without a ticket, and then they'll have to pay like the max amount or like the daily maximum or whatever. But anyways, you could have 100 people, you know, go in and out for free, and just one person at the very end pays the $25 or whatever the example is. So anyway, that would be like a more sophisticated kind of attack. Okay, so attack trees. What's the idea of them? The idea is to brainstorm these attacks, but then also put them into a format that I can give to you so you can understand what the attacks are. Okay, and it's also about sort of organizing the attacks so the attacks that are related to each other are close to each other in the tree. And then that also helps me think of new attacks. Once I get things sort of penciled into the tree, and I'm like, oh, this weight sensor, that's the thing that's stopping me, then all of a sudden I can focus on the weight sensor and maybe come up with 2 or 3 different attacks just on the weight sensor, okay? So it helps you brainstorm by kind of structuring. So if we throw this stuff into the attack tree, it might, this I did before, so it might not be exactly the same as what we came up with, off the top of our head, but it will be roughly the same. And this isn't meant to be a complete attack tree, okay? This is just a first glance at it. But anyway, so I would call the root node leave parking garage without paying. That's the adversary's goal. And then I might decide there's two kinds of attacks. There's the attacks on the ARM, and there's the attacks on the payment system, okay? There's probably more, but that's a good place to start. So if I expand the attacks on the ARM, I might say, okay, there's some sort of physical attack. You know, I could just drive around it, or I could just drive through it and break it. I could tailgate another car. We talked about that. I could trigger a power outage, and then it will fail open. So we talked about that. Another way to get the ARM to open is with the key. So I could get a picture of it, or I could do some social engineering, fold my ticket in half, those kinds of things. So here's some examples of someone just driving through an ARM. Here's like probably the worst like parking gate in the world. You can see there is a gate that stops you from driving down the road. Because it snowed recently, you can also see what most people do, which is just drive around it and not have to pay. And this is just showing you, 3D printed keys are as good as anything. Yeah.
The way you describe attack tree seems like you're just brainstorming as many attacks for. I wouldn't say all because you can't brainstorm all because there's always going to be an idea you are thinking of. So what's the criteria to make it like sensible?
Okay.
Is there a limitation or attack trees always subsets like forever and ever?
Okay. So an attack tree is actually meant to try and get you to consider all attacks. And the reason why it's like so broad, like when you do in a tree, there'll be like attacks all over the place, is it's meant to encourage the idea of thinking about attacking the system from different dimensions. I'm attacking the payment, I'm attacking the human, I'm attacking the electricity. It's meant to like kind of broaden your goal. So like any and all attacks that you can think of are great. The one criteria where you stop including things is when they become unrealistic. And there's no like hard line. I can't say, oh, that's realistic. Like driving through the ARM, is that realistic or not? Like we can debate about how realistic things are, but things that are like completely crazy or science fiction, you wouldn't normally put in the tree. So they should be, by some definition of plausibility, plausible, right? So that's the only thing that would limit you. You're going to put everything you can think of. The crazier your ideas are in terms of like looking at from different angles, that's encouraged. We want you to do that. The only thing we don't want you to do is not like do things that are super unrealistic. So it is subjective. So if everyone in the room, if I gave you this goal, your assignment one, I used to do this, your goal is to do this, everyone's going to come up with a different attack tree, but there's going to be commonalities between them, in my feeling, yeah? And most of these things you guys came up, I didn't tell you, some of you might have the notes printed out or something like that, but you more or less came up with all of these attacks anyways, right? And so there should be a lot of common ground between different attack trees. But again, it's an art, not just a science. Okay, and then on the payment side, we could use counterfeit money. We could say, oh, I paid even though you didn't actually pay. And if they can't figure out whether you paid or not, they might let you go. You could try and attack the ticket itself. You could tamper with it, print out a different QR code that would scan correctly. You could ruin it, and then maybe they'll let you out anyways. You could try and get the fresh ticket, but then you have the weight sensor. But then if you have a lot of friends, another thing, you could get a friend to pull up in a car, get the ticket, but then instead of driving in, they just back away and they leave with the ticket, give it to you, and then you can leave right away. Or you can do that kind of chaining attack. Okay, is this complete? No. The next attack tree, though, that we do, we're going to take 3 lectures. Rest of today, all of the next class, and a lot of the third class. And that's going to be a pretty complete attack tree. Okay, so you're going to see something that's very complete. We'll work on it over the next 3 lectures. But for now, anyways, I wanted to get you that idea of the attack tree. Okay, so everything is sort of organized in branches. Related attacks, like lots of friends are pulling up with a car and backing away. It's almost the same attack, right? but they all, they all attack the wait sensor, which is about getting the fresh ticket, which is about not paying, and so that's why they're together in the tree, okay? And then you can think of the story, right? Like, my goal is to leave the parking garage without paying. I can do that if I don't have to, if I can get the arm to open without actually paying, then it works. Whether I paid or not is encoded on the ticket, so if I could do something with the ticket, then that would work. And I'm going to tamper with the ticket, and then that's going to get me out. Okay, so it's sort of a story as you go from the root to the branch, you understand the story of the attack. So this is just the whole tree in one slide. Okay, questions about, this?
How many assumptions can I make about how the payment system works and all? For example, like let's say it's a office parking garage like the one Concordia has, and there is a account system wherein the money is deducted directly from your account instead of you having to pay the system on the spot.
Right.
So if let's say I make an assumption that the ticket serialization is not random, it is quite literally serial, and I just changed like a single number and that fits it so that another person's account is getting like the deduction of the payment.
Yeah.
So that is one attack I can think of if that system works like that.
Right.
But that depends on how I'm assuming the system works.
Yeah, yeah.
How to account for that.
Okay, so the main thing is you have to also think about why are you doing an attack tree in the first place? Like, someone asks you to do it, and it's more a question of like, who's asking you to do it and why, right? So if Concordia hired you to look at Concordia's exact system, they're like, lots of people have been leaving without paying, we can't figure out how they're doing it, right? Then you might go into that amount of detail and you'll look specifically at how Concordia implements it, right? If you're just writing an academic paper or doing a project, then you wouldn't look necessarily at the specific details. You might, unless if it was like a very common shared detail that would be the same across multiple systems. So it kind of depends on the audience for the attack tree, how much detail you go into, and there's no right or wrong answer. So, if you're asked to say something narrow, then you want to go into all those details. And if it's meant to be for a broader audience, then you don't want to go into all those details. Yeah. Another thing that reminds me of is sometimes you sort of stop because the attack shifts into like a well-studied area of attack. So like, for example, if my goal is to leave, I'm going to evade the robotic arm, there's an attendee, and I'm going to use social engineering. Well, that doesn't really tell the complete, like, what did I do on the social engineering? But then you could say, well, social engineering is its own tree. Like, we hit that node, and then that's its own whole. You could do a whole tree on social engineering itself. So sometimes that's why you stop as well. So like, on this HTTPS example where we're going, at a certain point, we'll hit DNS. DNS is important. And there's lots of ways of attacking DNS, and that's its own tree, and we're not going to pull that whole tree into our tree kind of thing. So that's another stopping criteria, is sometimes you just stop because you're like, oh, that's like a whole different attack at this point. Yeah. Okay, other questions about the tree? Okay, so we're going to do a more involved example, and it's going to be on this thing called HTTPS, so I'll spend a bit of time telling you what HTTPS is. Okay, so HTTPS is a protocol that's used when you visit a website. So you go to a website, and basically what you're doing is when you go to the website, you're asking, hey, give me index.html. And then the server is saying, here's the file, index.html. Here you go, right? And then your browser will read that file, and it will display it to you. And there might be images or references to other things, and then it might have to go and say, oh, I don't have that image, so now I have to go ask this. And the HTML will tell it where to go, and then it will go ask for the image. Okay? So it's like a network protocol thing. Okay? It's between a user and a server. And the term itself, HTTPS, stands for HTTP Secure, and it consists of two sub-protocols, okay? So the protocol just for asking for websites, going back and forth, is called HTTP, all right? And then if you want to do it with some security properties, then first off, you have to get the security from somewhere. And in this case, we're going to take it from cryptography. So we need some like cryptographic libraries and things like that, okay? So the protocol for the crypto is called SSL TLS, and you put the two together, you get HTTPS. So sometimes HTTPS is also called HTTP over SSL TLS, okay? So you can do HTTP with or without encryption. And you can use SSL TLS with or without HTTP. You can use it for HTTP, but you could also use it with other kinds of protocols as well. So they are like two separate kind of protocols that are being put together in this case to give you HTTPS. But it's now the most common way. It's the most common use of TLS is with HTTP, and more people use HTTPS than HTTP nowadays, I would say, which wasn't always true. Okay, just on the name, why is it SSL/TLS? It's just that it changed names. So SSL was born somewhere in the early 90s. Netscape was a company that made a browser. Before Microsoft or Apple had their own browsers, they had like one of the first browsers. And so they had this idea of doing some encryption. I think they worked with IBM. I don't remember the companies that were involved. They had like an internal version that was never released. I think there were some security issues. That was called SSL 1.0, but it was never made public, so we don't know what 1.0 looked like. And then they fixed them, and then they came out with SSL 2.0. Then it became 3.0, and then there was a shift where they changed the name to TLS. And then now we're at TLS 1.3. The numbering also went to 1.0, 1.1, 1.2. We're at 1.3. People are working on 1.4. So why the shift in names? There's kind of like two reasons. One is that it became important enough that it couldn't be a Netscape technology anymore. It had to be for everyone. And so they kind of turned control of it over to this organization that manages all network protocols. That's like a pretty open organization. If you've studied networking security, you've probably seen like standards that are from the IETF and things like that. So they're the organization that sort of oversees it. So when it switched from being a proprietary thing to an open protocol, they changed the name. And then if you've taken networking, you might know about the Cisco, or not Cisco, the, what's it called? The OSI model. Is that the right acronym? Does that sound right? Anyways, there's this abstraction of networks that's in about 7 layers. And one of them is called the session layer, and one's called the transport layer. And the crypto actually happens at the transport layer. It doesn't happen at the session layer. And so it was kind of a bad name for it. And so they kind of align the name with like where it should fit in that model. Most people, though, use a simpler like 4-layer model for thinking about networks. But anyways. Okay, what does it look like? So let's say you go to a website. You either go to a website over HTTPS or you go to a website over HTTP. Why do you end up on one instead of the other? We'll talk about that. Okay, so that will be coming in a couple slides. But let's say that you happen to end up on a website that's being served to you over the secure version of HTTP. Could you even know it as the user? Do you know it, or is it just something that happens in the background? And if you ran a packet analyzer or something like that, you could figure out whether it's using it or not. But otherwise, then you wouldn't know. And so browsers will actually tell you whether you're using it or not. Okay, they're going to communicate it to you. And there's 2 ways that they communicate it to you. One of them is with this lock icon that appears. And then if you looked at the URL, you would see that it's HTTPS : / as opposed to HTTP. Okay, and these 2 things are almost one-to-one, but for subtle reasons, they're not exactly one-to-one. Like it would be possible to have a URL that's HTTPS and the lock not appear. Vice versa is impossible. So if the lock's there, it's definitely over HTTPS. But there's a little more than goes into the lock other than you typed in HTTPS : / There's some checks that have to occur, and don't worry, we'll go through all the details of those checks. Okay, so this is what it looks like. And different browsers will do it different ways. And recently, like in the last year, there's been some proposals to change it. It may already, I think it's in Chrome, and I don't know if it's in Safari. I could actually probably check it. But there's a thought to actually remove the lock. And by default, So like the old thinking was that the default is sort of like you don't get the secure version. And then if you get the secure version, that's like an exceptional thing. And so we're going to show you a lock in that case. Now the web's kind of like security is more at the forefront. And browsers want every website to be secure. And so in order to encourage it, what they're going to do is they're going to just get rid of the lock. And so if you just go to a website and there's nothing, then it's secure. But if it's not secure, then they're going to show you a scary warning or like a warning sign or something like that. Yeah. So instead of enforcing, yeah. So I don't know what my version of Safari. Unfortunately, Concordia kind of stops me from keeping it up to date. But yeah, we're still using the lock in Safari. But I think with Chrome now, there's no lock. No lock means it's secure, and a scary warning means it's not secure. Okay, how do you end up on the HTTPS version rather than the HTTP version? Okay, the first thing is it your choice? Do you get to choose whether to use it or not? And the answer is, well, it actually starts with the website. So the website has to offer it. They have to have their server configured to run the cryptography. And if their server is not configured to run it, then you can't get the HTTPS version. Okay, so the change has to start at the website. Okay. Now, a website has a choice where it could have just HTTPS, no HTTPS. Sorry, just HTTP, no HTTPS. Vice versa, it could offer HTTPS. But if it offers HTTPS, it also has to decide, well, am I going to offer both, right? Like maybe there's people that have old browsers or they think it's slow to have the secure version or whatever. And so we'll give people kind of like the choice. Or sometimes they might only have HTTPS, okay? So the website will be configured one of those types of ways, okay? From a user perspective, how do you make sure that, like say I only want to go to websites if it has HTTPS. How do you make sure of it? There's a couple different ways. So one way is that you explicitly type it in. And then the website will either, like you might get an error message that would say, oh, this website doesn't support it, or you would get the secure version, okay? So that's an easy way. But most of us aren't typing in URLs, or if we want to go to Google, we're not going to type http://www.google.com. We're just going to type GOOO, and then Safari's going to say, oh, you want to go to Google, and we hit enter, and we end up on Google. Another thing is, let's say you click a link. So like I'm on website A, I click a link, and then I go to website B. Am I going to the HTTP version or the HTTPS version in that case? Okay, so it depends on the link. So it's actually the person who programmed the website of website A, they're making the decision for you of whether they put the HTTPS in that link or not, okay? So you're at the mercy of the website that you're following the link from. Another thing, let me skip down to the last one. There's also redirections that can happen. So you might go to a web server over HTTP, and then they might say, oh, actually, we use HTTPS. And so they'll tell your browser, go to the HTTPS version. So the message will go back to your browser, then your browser will try the HTTPS version. Now the problem with this is that if there's an adversary in the middle, right, when that redirection happens, the redirection is not happening over the secure version, it's happening over the insecure version. So they can try and disrupt that process from happening. But anyways, we'll get to those details later. Another thing that happens is you basically cannot go to Google not over HTTPS. They probably don't even support it. They're probably one of those websites. But every browser knows that Google uses HTTPS. So if you even type Google in, or most browsers have like a search bar that's like part of the browser user interface that automatically redirects you to Google if that's your configured search engine. And so like that idea that Google operates only over HTTPS is like baked into the browser itself. Okay, and that's because Google is a huge, massive site, and everybody knows about it.
So it's a decision of the site or the browser?
So then, in that case, it was the decision of is more like the companies both behind the site, like behind Google themselves and behind the browser. So like Google is actually a special case because they're both of those companies. They have a very popular browser, Chrome, and they also have a very popular website, Google, right? And so they'll do stuff in Chrome. We'll see this actually as we go through these lectures, that Chrome often leads the way in terms of security because they control the most popular website on the internet, and they control one of the biggest browsers as well. And so they can do changes, and then other people will follow suit. But anyways, it would be the decision of the people designing the web browser to say that website's big enough, and we know the people there, and we know they want us, like we know Wikipedia, we know they want us to go over HTTPS, so we're going to put that in the browser so the user can't possibly not go. Yeah. And then websites can also set that. So you can set a flag. So if you come to my website for the first time, I can put a flag that gets sent to your browser, and I tell your browser, remember that I do HTTPS. I want you to remember that for 30 days. I want you to remember that for 1 year. And if you ever come back, if the user even tells you, or you follow a link or whatever, and you try and go to HTTP, I want you to stop that process, switch to HTTPS, and then come to me. Okay, so I can set those flags. Now again, there's a small problem, which is that if there's an adversary tampering with things, they can tamper it before the flag is set, or when the website's trying to set the flag, that's when the adversary tampers with it, and they make sure that the flag never gets set, right? Then you're out of luck, okay? So we have a lot of security systems where if you can talk to the right system the first time, you can set up a bunch of configuration so that you can never be attacked again, okay? But if the adversary is present the first time you talk and they can mess with the configuration, then they can mess with it so that it's always insecure, or at least there's no guarantee that it's secure. Okay, so those kinds of systems we call trust on first use, meaning that you trust that you're getting the right person the first time you talk to them. And then if you're able to do that, then you can set up all sorts of security to protect future communications. But if you can't, then you get no security at all. Okay, so this is like a reasonable real world assumption. It's not great from a security perspective. We'd rather not have to make that assumption, but it works well enough in real world examples. Yeah.
The adversary cannot change that flag after it is set?
So yeah, that's right. Yeah. So your browser will remember it, and so if the website comes back and says, "Oh, by the way, that flag, like change it," they'll be like, "No, because you look like an adversary who's trying to change the flag." Yeah. So that's why it will ignore it. And so you can also, actually, when this sort of protocols first came out, people made mistakes. So they like configured it wrong, and then their users had this flag set, and then they couldn't do anything for like a year or two. And yeah, so that happens as well. Okay.
But there can be chances like when you are on a HTTPS page, there can be iframes with HTTP links basically. Like a website can show a website with HTTP links.
Okay, good. So hold that thought. So websites often weave content together. So like a website, like when you download a website, it doesn't actually all come from one source. So it's embedding images, scripts from other places. It has iframes, and then other web servers are putting stuff in the iframes. And so when you look at a website, it's not like it came from a single place, right? And so then you can ask the question, well, what if some of the stuff is coming down over HTTPS and some of it's coming down over HTTP? Do you show the lock or not, right? And so that's a great question. We'll answer it later. But yeah, it's the right question to ask. Okay, so what do we want from this property? So far we've sort of vaguely said we want it to be secure. Okay, and security normally what we think of is an attacker that's attacking the communication. They're in the middle of the communication. Back when we always called people men. It's sexist now, but anyways, it was named the man in the middle attack. And so I'll just say MITM because it's pretty standard, but it could be a woman, it could be anyone, any gender in the middle. Okay, so this is the sort of scenario. So what are we trying to stop the attacker from doing? Or what's the attacker trying to do and what don't we want them to do? Like what does it actually mean in terms of security? What does it mean in terms of stride? Is this a spoofing thing, a tampering thing, an information disclosure thing? escalation of privilege? Like what exactly are we trying to do here?
You could do information disclosure and tampering.
Okay. So it could be more than one thing, and so that's the correct answer. So the first one, the obvious one that most of us think of is information disclosure or confidentiality. So we want secrets that are passed over this secure channel to be kept secret from that adversary. So the adversary can't read it. The adversary knows that messages are being sent, okay? But they can't read them. Why can't they read them? Well, there's this encryption thing, and we'll talk a little bit about what that exactly means, okay? What was the other property? Tampering. Okay, so what does that mean? Okay, so the adversary shouldn't be able to change the message. Now, if it's encrypted and they can't read it, isn't that good enough? You can't change something if you can't even read it anyways. Okay, sounds reasonable. I see some nodding of the heads. Once you take crypto, you'll realize that that's not enough, okay? There are ways of attacking encrypted systems where even though you don't know the message that you're attacking, you can do things to it and you know what you're doing. So like an easy example would be, let's say there's a message that has my salary going from my boss to the other boss across the wire. I don't know what that number is. I can't read it. It's encrypted. But if I want to double it, no problem. I just multiply a 2 into the ciphertext. And then when they decrypt on the other end, they decrypt the number multiplied by 2. Okay? So like a crypto system like RSA, that's actually possible. So you can, we call them malleable. They're malleable encryption schemes, okay? So just because the adversary can't see it because it's encrypted, that doesn't mean they can't tamper with it. You can sometimes tamper with systems in a meaningful way, even though you don't know what the data is that you're tampering with. So we need integrity as an extra property, okay? And so integrity will roughly say that the adversary is not allowed to change it. Now, we can't actually stop the adversary from changing the messages. They're in the middle, they can switch the order of packets, or they can replace this packet, or they can drop it. They can tamper with it, okay? We can't stop them from tampering it. We can't prevent them from tampering it, but what we can do is detect it, which is more or less good enough, okay? So they can do the tampering they want, but then when Concordia decrypts it, then they'll say, oh, that's wrong. There's something went wrong, there's something missing, or I'm not going to accept that because it didn't pass the tampering check. Okay, so that's what it means. So we talk about message confidentiality, keeping secret. We talk about message integrity, meaning that you can detect any modification that's made. Even if it's as small as flipping a single bit, you're going to be able to detect that. You won't know what the modification is, but you'll reject it. You'll say that was modified, it's not the original. And then usually you would ask for it again because sometimes there's like noise on the wire or something like that. Okay, any other properties?
Stop this person from accessing the website if you are using.
Okay, so denial of service. So that's another property. So the adversary can just drop all packets. Okay, so that's an attack. It does work on HTTPS, and HTTPS does nothing to defend against that. So that's an attack that we just accept. So we say the adversary can do that. We don't know how to stop it, and so we'll just accept it. Yeah. Whereas the integrity and confidentiality, we'll try and do something about it. Yeah.
Redirect the message to some malicious site.
Okay, so say it again. So redirect or reject.
Redirect it to some malicious site.
Okay, great. Okay, let me rephrase your point slightly different, which is we have this. Okay, I'm going to introduce this idea of a tunnel. So it's kind of like a secure tunnel, right? You can't see what's going on. You can't change any messages. Where does the tunnel end in this picture? It ends at Concordia, right? Does the user know that it ends at Concordia and it's not being redirected somewhere else? Okay, so how do I'm the user, I'm just throwing my messages into the secure tunnel. I know they're bulletproof when they're in the tunnel. No one can change them, but at some point that tunnel is going to end because someone has to read it, right? So how do I know I don't have a tunnel just to the adversary? And so I'm securely delivering my messages to the adversary. Okay, so the third property we want is, we call it authentication or server authentication, and we want to know where the tunnel ends. Okay, so we want to know that the tunnel, You can't read messages that go across the tunnel. You cannot modify messages that go across the tunnel without being able to detect it. And we know where the tunnel ends. If we can do all three of those things, then this is a good, we can't do anything about denial of service, so we're not trying to attack that, but it's a pretty good protocol. Okay, so that's the goal of HTTPS. So confidentiality, you can't read data even if you, the adversary, are on the path. Integrity, if the adversary modifies it, you can detect it. And server authentication, the user knows where the tunnel ends. Okay, so how do we do all of these three? We'll kind of go through them, but I'll give you a rough view. Message confidentiality, we'll use something from cryptography called encryption. You'll learn about it in 6.1.10. You probably already sort of know what encryption is roughly, and it's exactly what it sounds like. So there's some keys, and if you have the right key, you can decrypt it, and if you don't have the right key, you can't. Adversary doesn't have the right key. Concordia does have the right key, and that's how we deal with it. Message integrity, you can think of digital signatures. They use a lighter weight version called MAX, message authentication codes. Again, it's a crypto subject. You're going to learn about in crypto. I'm not going to teach it to you now. And if you put the two of them together, we call it authenticated encryption or CCA2 secure encryption. And so the most famous algorithm that might be used that has both of those properties is called AES GCM. So anyways, eventually you'll take crypto and those words might mean something to you. Okay, so that takes care of these two. Server authentication is a mess. Okay, how do we figure out how the tunnel ends? That is not a problem that's easy to solve, and a lot of our attack tree is going to be built up on the fact that it's kind of messy how you figure that out. So we'll spend some time on that. Maybe not today, but starting next week. Okay, this is just illustrating the idea that if you don't have the third property, you don't know where the tunnel ends, then the whole system sort of breaks, right? Like if the adversary can end the tunnel at them, they can then reestablish the tunnel to Concordia, and in the middle they can read everything, they can change the messages, right? And so like you might as well not have a tunnel, right? The tunnel serves no purpose other than maybe stopping another adversary from jumping in the middle again. Okay, so without this third property, it's not a useful system. Okay, so what we're going to do is we're going to build an attack tree, and what we're going to do is remember an attack tree. You look at one system, so parking lot HTTPS, but you actually look at one property of one system. So if we want to do attack tree attacking the confidentiality of HTTPS, that would be one attack tree. If we want to attack the integrity, that would be a second attack tree. And if we want to attack server authentication, that would be a third one, okay? But maybe attacking integrity could help you break confidentiality. Then those attacks could fit in the confidentiality tree. Or similarly, we saw that if the adversary can have the tunnel end at them, then they can break integrity and confidentiality. So an attack tree that's just about confidentiality will also include some attacks on these two, but their secondary goals are not the primary goal of the attacker, okay? So the attack tree that we're going to build is very simple. It's just, we're going to assume that the attacker is somewhere in the middle, okay? So that's a given. How do they get in the middle? I don't know. They could be Concordia, like say I put up a fake Wi-Fi router and I call it Concordia University and a lot of you connect to it, thinking that it's the real Wi-Fi. Right? It could be that I'm an ISP or I have access to the ISP or I broke like the server of the ISP and put malware on it, or maybe I have malware on your machine and I intercepted it before it even leaves your machine. There's lots of different options for how I get in the middle. We're not going to worry about that. Okay, we're just going to assume that the adversary is already in the middle. And the adversary's goal is very simple. They're in the middle. They want to listen in. They want to know when you send your password or your credit card number over that channel, they want to know what your password is. Okay? That's their one and only goal. And so that's the attack tree that we're going to try and build. Okay? So what are all the ways that the adversary could achieve that goal, under different types of scenarios? And you might think that this sounds like the makings of a pretty empty tree, right? HTTPS is pretty secure. There might be 2 or 3 attacks, maybe something that worked in the 1980s but doesn't work today. But I'm here to tell you that we're going to have a very complete attack tree, and there's going to be a lot of different ways of attacking it. And it's going to get a little crazy in terms of they're not going to be like crypto attacks, right? They're going to be social engineering or like attacking governments and like all sorts of weird places that you wouldn't think that you would go when you're analyzing a network protocol. But that's what a good attack tree is good at. It's good at trying to get you to think broadly about security and think about all the possible attacks. Okay, so our root node is going to look like this. We're going to observe traffic sent over HTTPS from an MITM position. And what I'm going to do is I'm going to break it into three rough categories. Okay? The first category is pretend we're sitting outside of the tunnel. I mentioned that, what stops you, well, you can actually, a good way to start is with the tip that I gave you, which is what stops you from just doing this? Your goal is to read it, so why can't you just read it, right? So you might say, well, there's this encryption, right? I can't get the encryption. And so I'll say, okay, that's great. First off, you are seeing the encrypted messages go back and forth. Does that really tell you nothing? Like, is the encryption so good that you learn absolutely nothing? So that's the first question we'll consider. Is there stuff that you could learn even though it is encrypted? I'm not actually going to break the tunnel, but I am seeing some stuff go back and forth. I don't know what it is, but like, can I really do nothing about it? Okay, so that will be the first class of attacks. The second will be, can I break the crypto? Okay, this, I'll give you the high level ideas. I'm not going to teach you crypto. And I'm not going to assume that you've taken a crypto course. And these attacks get like fairly detailed, like in terms of the exact algorithms that are used and how you break them. But I will give you the names of attacks. And if this is of interest to you, you can look into them further for like projects for this course or your crypto course. And then the third kind of category of attacks will be, can I get the tunnel pointed at me? If I can be the endpoint of the tunnel as the adversary, then I can read everything that's sent over the tunnel because it's ending at me instead of ending at the website. And I can relay information to the website so I can make it look, the user thinks they're interacting with the real website because I'm relaying everything back and forth, but I am in the middle like reading it all. Okay, and so that will be the third kind of category. Okay, so before we jump into this first category, it's maybe a good time for a break. So why don't we take 10 minutes and come back at 10 after, and then we'll jump into this first category. All right, we'll get started again. Okay. All right, so we have three high-level goals for seeing what's in the middle of an HTTPS connection if we find ourselves in the middle of such a connection. And we're going to start with the top one, which is we're going to stay outside of the tunnel. We're not actually going to try and break into the tunnel, but we are seeing sort of stuff go by anyways. And so we're going to just think about like, what can we learn from that, if anything? Okay, so the sub-goal is we're going to see if we can recover some amount of the data that's going back and forth from observing from externally or from outside of the tunnel. And we're content with partial data. So we probably aren't going to be able to see everything, but maybe we can see some small things or I don't know, we'll see as we go through. Okay, so for this branch of the tree up here in number 1, we're going to assume that HTTPS works flawlessly. There's no problem with HTTPS itself. It works perfectly. And even if it works perfectly, can we still sort of achieve our goal or not? Okay, so is the security that it offers actually complete? Is it comprehensive? Or can we still learn things? And if we can learn things here, then it arguably, like, HTTPS didn't solve that problem. It wasn't a goal of theirs to solve their problem, okay? But we don't care as adversaries. As long as we're learning stuff, we don't care whether that was supposed to be covered or not by HTTPS. Okay, so here's Alice. She's going to concordia.ca. What's the very first thing that her computer does? She types in concordia.ca. She presses the enter key on her browser. What's the first thing that happens outside of her computer? Okay, so we can't literally go to concordia.ca. We have a packet that's going to be like, hey, give me index.html at concordia.ca. We can think of it as an envelope, so that request, give me index.html, is like the letter that's inside the envelope, and then concordia.ca is the address that's on the envelope. We drop that in the mail, and it ends up at Concordia. The problem is that the internet doesn't know how to route, it doesn't know where concordia.ca is. Okay, so the internet is organized by numbers, not by names. And so if it's a number, the number's hierarchical. So it means that like the top part of the number, everything that has the same top part of the number goes to one place. Then they look at the second part of the number and split it up. And then they look at the third place, and eventually it ends up in the right place. Okay, so we need to address it with a number, not a name. How do we do it? Well, there's a big directory of every number and every name. Okay, it's organized by name. So you start with the name, and then it will tell you the number. You can do it in reverse because it's a database. You can reverse it, but usually you're going from name to number. Okay, that system's called DNS. So first thing I'm going to do is I'm going to ask DNS. Now, what is that? Like, what is DNS? Where is it? Like, so I'm here. I'm at Concordia. Or I'm at home maybe trying to connect to Concordia. Like DNS is it's a computer, it's somewhere, like where is it, who owns it? Okay, so it depends is the broadest answer. But the simplest answer is it's something that's given to you by the person that gave you your internet access. So if I'm at Concordia and I connect to the network, it tells me, okay, here's your address for your computer while you're connected. And by the way, here's the directory that we're giving to you to use. So Concordia would probably have their own directory. If I'm at home, I'm on Videotron. Videotron has that directory. Okay, so it's my internet. I'm paying Videotron. I'm paying them to maintain one of these directories for me, so I'll ask their directory. Now, if I really wanted to, could I, I'm on Videotron, and Videotron's like, here, use my DNS. Could I use Google's instead? Yeah, so the answer is yes. So I can use any DNS server. And in fact, Google offers that. So if you put in 8.8.8.8 or 8.8.4.4 in any DNS resolver, then you'll access Google's DNS. Okay? Why do they do that? Why does Google do that? It's very, very kind of Google, right, to offer DNS to anyone who wants it. Well, they can see every website that you go to. They might not know who you are because they see an IP address, but every single website you go to, you have to ask Google now, what's the IP address? And so they have really good detailed data on like what individual IP addresses are asking for. Then you go and you log into Gmail from that IP address, and now they know who you are. Module, a couple details, like multiple people might be at the same IP address. But anyways, okay, so that's DNS. DNS, how does Videotron or Google figure out what the IP address is?
It's a hierarchical system that .ca is known by some root servers, and then they know where Concordia is, and then they redirect you to Concordia's DNS server, and then you ask Concordia's DNS server for the web server that you're looking for.
Okay. So DNS is an entire system. It's not just like that one server that's sitting there. Everything that server knows, it learned from somewhere else. And those servers learned it from somewhere else. And it is organized like someone will be authoritative over all of .ca and someone will be authoritative over .com. And sometimes you'll get asked a question as a server, you don't know the answer, then you have to go and ask your friends. And then you figure out the answer and you give it back to the user, okay? Most of those details we can abstract away. Okay, we don't care. It could be a single server. It could be a complete system. We don't really care. It sort of impacts the security, like if you want to go in and attack DNS and get fake records or fake IP addresses associated, then those details could matter a lot, and depending on how you want to do it. But for our purposes, we'll just assume it's this sort of unified thing, okay? One exception, the one thing that we'll pay attention to is how did it happen in the very first place? Like somehow Concordia.ca, like if I'm Concordia.ca, I set my server up and I give it an IP address. I have to have the IP address, but like I maybe have a whole bunch of IP addresses and I decide of all the 1,000 IP addresses I own, I'm giving the server this one. So at that point in the world, I'm the only person that knows Concordia.ca and this IP address, right? Eventually, everyone in DNS will know it. But how do I get from me being the only person to know it and everyone in DNS to know it? Who's the first person I tell? I tell one person, then they'll gossip it around all of DNS. So the person I tell is the person who gave me that domain. So in order to own Concordia.ca, I had to buy that. And I bought it from a place called the domain registrar, okay? And they're going to be in charge of because they sold it to me, they're in charge of my DNS record. Okay, so any change that I want to make, I have to make through them. There are ways of like changing it. Like I could say, I don't like you guys, I don't like GoDaddy anymore, I'm going to go somewhere else. Okay, but basically to keep things simple, you're always going back to your domain registrar. Okay, so these details will matter a little bit later. We'll review them when they matter, but for now they don't matter. Okay, let's say there's an adversary sitting between me and DNS. Is that possible? Yeah, it's actually pretty easy, right? Most adversaries actually probably would be sitting there because they'll be listening to your Wi-Fi, or they'll be the Wi-Fi router itself, or, like most adversaries are usually close to you rather than being close to the other end. But it depends on what type of adversary. So yeah, an adversary absolutely could be between you and DNS. Does DNS happen over encryption? Is there a secure tunnel? What if the adversary just changes the IP address and points it at themselves? They could. Any other ideas? Anyone want to disagree with that? Okay, so the answer is more or less they could. So that's 90% true. DNS originally did not run over an encryption or signatures or anything like that. So it's not running over a secure tunnel. Any adversary in the middle can disrupt it. They can change anything they see. They can see what you're looking at, what IP addresses you're asking for, all of that type of stuff. Okay. Why is that allowed to happen? Okay. Well, the internet people don't like it. Okay. The problem is they tried to fix it. They tried to fix it by putting secure tunnels between it. So there's a big standard called DNSSEC, which is the secure version of DNS. And the problem is it's just so onerous and it's big. And actually we saw DNSSEC, maybe you remember in the very first lecture, where this is one of those things that you can do an amplification attack because you say, hey, what's Concordia.ca's IP address? And instead of getting back, 4 256-bit numbers, you get back a certificate that's signed by someone else, that's signed by someone else, that's signed by someone else, and the thing that you get back is like huge, right? And so when you have lots and lots of people asking DNS all the time for IP addresses and you're passing around all this big cryptographic information, then the servers go down and things like that. So more or less like DNSSEC never got off the ground because it's too much overhead for that protocol. Okay, so you may or may not use DNSSEC, but for the purposes of this class, we'll just assume that you probably you're probably using just DNS without any security at all. Okay, so one thing the adversary, because our attack tree is about learning what the data is, we won't worry about so much about the changing data and things like that, but the adversary can know what IP address or what domain you're visiting. Okay, so if the adversary is sitting here, even if ultimately we have a secure tunnel, right? They do know that while you queried Concordia.ca for their IP addresses, you're probably going to Concordia.ca. Okay, and so sometimes, anyways, I'll circle back to that. Now let's say the adversary is in the middle, okay, and so now the data is going through this magic secure tunnel using a lot of fancy cryptography. Does the adversary sitting here know what domain you're going to? Do they know that you're going to Concordia.ca?
It depends on the TLS version that they're using. So if they're using TLS 1.2, the SNI that the client is requesting is not encrypted in the beginning. So they could learn what you're requesting. And if it is on, let's say, TLS 1.3, they could force you, because they're in them as well, they could force you to use 1.2 when they go.
Okay, so there's two things there. So one thing is different version numbers might encrypt different information. What we're talking about, though, ultimately won't be the indicator that you're talking about, SNI, right? It's not the right answer for that question. But the other thing that you mentioned that's interesting that we'll circle back to is what we're going to call downgrade attacks. So a downgrade is like, hey, server, I want to run TLS 1.3, and the adversary switches it to, hey, I want to run TLS 1.2, and the server's like, great, let's do 1.2, and it sends you all this information. And so, yeah, we'll talk about those as well. Okay, but there's a simpler answer to this question. So does the adversary in the middle know that you're going to Concordia.ca? Let's be to avoid the DNS thing. Do they know that at least that you're going to 132.205.244.70? Why?
Because the destination of the packet is always there.
Okay, the packet could not get to Concordia.ca if no one could tell where it's going. Okay. It's not the negotiation, so we'll assume the negotiation has already happened. But the point is, again, think of the envelope. You're putting some data inside the envelope that's going to be encrypted. You're going to drop it in the mail, but in order for it to get to the right place, the address has to be on the outside of the envelope. Okay? The address isn't on the outside of the envelope. No one knows where to send it. Okay? So the IP address is the one, at least one of the things that can't be inside the envelope. It has to be in the clear. Otherwise, you can't route it. Okay? And turning an IP address back into a domain is just about like reversing the DNS database, and so you can do that trivially. Most DNS servers will do it for you, called reverse DNS. So you can just say, here's an IP address, show me all the domains that match that particular thing. Okay? So the adversary can learn where the user is going, whether they're sitting between the DNS server or if they're on the wire. They can be in either position, they learn the same information. Okay, is that something for our attack tree? Like, is that significant, or does it not matter what domains people are going to? And so in some circumstances, it absolutely matters, right? Like if I see you going to, I don't know, wikileaks.org, that tells me something about you. I can't see your traffic. I don't know what you're doing on the website. I don't know what videos you're watching or anything like that, but I do know that you're going to that domain, right? And that could be enough for me to, be concerned or whatever. If I'm an employer, I might be concerned about that. If I'm a government that's spying on their citizens, just going to certain domains would be enough for me to maybe launch an investigation or something like that. Okay? So the fact that domains are not hidden by HTTPS isn't well understood by users. They see the lock and they're told everything you do is secure. They don't always know, anyone that's watching knows exactly what website you're going to, okay? It's true that you type your password into it, they can't read your password out, right? But they do know that you're typing a password into that website, or they know you're doing something. Let's leave it vaguely as you're doing something with that particular website, okay? So just knowing the domains that people go to, that there could be repercussions in certain circumstances just for visiting certain kinds of domains. Okay. Now let's think about, there's somewhere else I want to go in a direction. So let's think about this website here. So this is Wikipedia. You can see, maybe not very clearly because it's kind of small, but this is being served over HTTPS. Okay? It's a website about CF Montreal, local soccer team. Okay. So as we've established, if an adversary is sitting in the middle, looking at me going to this website, do they know I'm on Wikipedia? They do. right? Because they can see the IP address and they can reverse it, and so they know that I'm on Wikipedia, okay? Do they know that I'm looking at CF Montreal article as opposed to any other article that could be on Wikipedia? Maybe, maybe not, okay? So what we're talking about here is the difference between the domain and the path, if you will, okay? The file, once you're at the domain, then you ask for the file, okay? Now, we said that, you know, the domain has to be on the outside of the envelope, otherwise the packet won't get where it's going. Does that file name have to be on the outside of the envelope? No, it can go to Wikipedia, Wikipedia can decrypt it, then they learn the path, and then they're like, okay, this is the file that the person wants, and then send it, okay? So as a general rule, if it doesn't need to be on the outside of the envelope, it's not going to be there. So HTTPS is going to put the least amount of information on the outside of the envelope. So just the bare minimum to get the packet where it needs to give, and then it's not going to give anything more, okay? So the high-level answer to the question is that no, an adversary in the middle doesn't know that I'm looking at this Wikipedia page. They know I'm on Wikipedia doing something, but they don't know that I'm looking at CF Montreal. Okay. Now, this is sort of what the network trace might look like. So I'll ask DNS, I'll get the IP address. Wikipedia will say, okay, you know, I want to get this path name. Wikipedia will decrypt it. And then they'll say, okay, great, I have this. The first thing they'll send me is the root website, which is usually in HTML. It could be PHP or something else, but we'll call it index.html. And from that file, it will give me instructions on how to get everything else that's on this website, okay? Because, like, for example, this image won't be in index.html. Like, the image itself will not be there. Okay, what will be in index.html is a reference or a link to the image, right? So then I'll follow that link and then I'll grab the image later as an image file, not as, theoretically you could like dump an image into binary and encode it into the HTML itself. But anyway, that's generally not how the web works. Okay, so I'll download index.html, and then as I'm reading the HTML, it will say, I want you to put a picture here. By the way, this picture is at this server, upload.wikipedia.org. That's a different server than wikipedia.org or n.wikipedia.org. Are these have the same IP address? They both end in wikipedia.org. Okay, so not necessarily. They have the option of having different IP addresses. So every subdomain is its own thing, okay? It might as well be completely different websites as far as the web is concerned, okay? And then, so then I'll get the logo, and we're going to assume that this happens over HTTPS, and a little later in the class we'll start thinking about what happens if some of this stuff is coming over secure channels and some of it isn't, and you're kind of weaving it together. But for now, we're going to assume that the adversary maybe is close to wikipedia.org, maybe they're using the same IP address, and so the adversary can see all of this stuff in the middle. Okay, so modern websites, and Wikipedia is actually a very clean website. Okay, very clean because they host all their own media and things like that. Okay, most websites you go, it's kind of a disaster. They're pulling stuff in from everywhere, and ads from here and scripting from here. And we're going to keep looking at pictures like this one. This is a picture you can generate yourself. If you just go to any website, you might have to enable developer tools, but you have this inspect element thing. And then if you go through the tabs, there's a bunch of interesting stuff. But this tab here shows you all the files that were used in order to create this website that I'm looking at, okay? So you can see that there's probably between 100 and 200 just by a skim. Actually, it says 124 exactly. So there's 124 little files on this article, okay? So like a lot of them would be like here's all the players and here's the flags of the countries that they're from. And so each one of those flags is its own file, that type of thing. So you can see how it's easy to get to hundreds of media. Okay, now let's go through these one by one. So the actual name of the file itself would that be something that you could see if you're an adversary and it's being served over a secure connection, over an HTTPS connection? Okay. Does it need to be on the back outside of the envelope? It doesn't. Okay. So this is something that would be protected by encryption. So you wouldn't be able, you could see that the person's going to upload.wikimedia.org. You can see a packet go there. You can see another packet come back, but you don't know what it was that they asked for. You don't know the file name of it. Okay. The domain, we established that you do know that. Okay. Otherwise, the packet couldn't get where it's going. So you do know that. The adversary does know that it's HTTPS. Okay, so there is this negotiation handshake thing. We'll come back to that more in the next when we try and break into the tunnel. But there's no secret about it. It's not like websites. The adversary doesn't know what the protocol is. Okay, they know exactly what's going on. They know it's encrypted. Okay. Files have different types. So, there's HTML files, there's JavaScript, there's some stuff for like setting fonts and layouts. There's images, so PNG, SVG are images. If I go and I ask for a particular image here, does the adversary that's sitting here, do they know that I'm getting a PNG file as opposed to any other file? No. Okay, so that's going to be on the inside of the envelope as well. Okay, so the name of the file is in the envelope. The kind of file it is in the envelope. The file itself, that it's this exact logo, that's also inside the envelope. Okay, so basically the only thing that's on the outside of the envelope is the domain that I'm getting it from. Okay. What else do we have? So we have who initiated it. And then the rest is just about like how long did it take to come down and how big the file is. Actually, how big the file is. Is that something the adversary knows? Okay, the time, yes. They do know the time. So they know when, they know the order in which you ask for things. They don't know what you're asking for, but they do know the order. And they know sort of roughly how long it took for the server to respond.
The exact size would not be known, but the approximate size would be known.
Okay, and what's your justification for that?
Because
Not to put you on the
packets are
spot,
of
but
equal sizes, right? So that is the reason. They can be the last packet, like the packet is not filled with more data.
okay. So the higher level answer is it has to do with the encryption. So if I have a message and I encrypt it, I have a plain text, I turn it into a ciphertext. Is that a operation that keeps the length the same, or is it something that changes the length? And if it changes it, does it change it a little or a lot? Okay. And so until you take encryption, you might not know this. But encryption generally is length preserving roughly. Okay, so if I have something that's 2.21 kilobytes as plain text and I encrypt it, my ciphertext is going to be roughly that size, 2.21. Okay, the reason that I say roughly is that encryption scheme will round up a bit. So it depends on the encryption that's used. There's something called stream ciphers. It would only round up to the nearest byte. So it would actually be exactly the same size. There's something called block ciphers. They round up to the nearest 256 bits, depends on the configuration of it. But that's like such a small difference relative to the size of the file that they're more or less the same size. Okay? Why can't we just make everything the same size? So the encryption algorithm could do that. Okay, so it's a lot of wasted network stuff. We'd have to pick the biggest thing on this list. First, we wouldn't even know what the biggest thing is, right, until we downloaded everything. But then if we decided that the biggest thing is 80 or I guess some of these might be in megabytes. They're all in kilobytes. If the biggest thing is 80, then even something that's 1.27, we would artificially pad it out so it's 80 kilobytes. But now we're sending like 10 times, 100 times the amount of data that we need to send. Okay, so it's ridiculous to do. Now, some systems do that. Some fancier encryption systems that are really concerned about anonymity and untraceability and things like that, they may have chunks. Packet size or things are always a certain chunk. So they might have slightly different chunks, but they make everything like uniform within certain like buckets. in terms of size. But anyway, HTTPS does none of that type of stuff, okay? So in other words, if I download this file, this .png file, the adversary knows I'm doing something with Wikimedia. It doesn't know that I'm actually getting an image. It doesn't know the name of the image. It can't see the image itself, but it can see the size of it, okay? What if you knew the size of every image on upload.wikimedia.org, and there's exactly one image that's 2.21 kilobytes. Every other image is slightly different in terms of size. Do you know which image I downloaded? So the answer is yes. I mean, you can infer it. It's not because you can see it, it's encrypted, but the length in that case tells you what it is, okay? So keep that in mind. All right, so this is encrypted, this can be seen, and the size can be seen. Okay, so just to recap, when HTTPS is working flawlessly, there's no problem with HTTPS itself, okay? The adversary still knows some things, okay? They know that the user is going to wikipedia.org. They don't know what article they're looking at, but they know that they're on wikipedia.org, okay? If I'm on that CF Montreal site, they know that I have 87 here. I know it's a slightly different number, but pretend there's 87 images on that website or other resources. The adversary can see that. They can see that I create 87 outbound requests and I ask for something and something comes back to me. They don't know what I'm asking for. Is it an image? Is it a JavaScript? They don't know what it is. They can't read the file name, but they do know that I'm making exactly 87 requests. Now, some of these images might be cached. I might have them already because I was browsing Wikipedia yesterday, and so I happen to have some of them. So this number is subject to caching, but it would be something like roughly around 87. And further than that, they also know the size of everything that I'm asking for, okay? And they could also kind of look at the order. They know the timing, like I asked for this before I asked for this, right? And when you parse an HTML file, you tend to do it from top to bottom. So my browser is going to ask for this image, right, before it gets around to asking for this image, because this image is way down on the website, okay? Again, there's race conditions and things might be slightly different, okay? But there is a rough pattern or fingerprint to what this website looks like, even if you're just looking at encrypted traffic, okay? Not every article on Wikipedia is going to have roughly 87 resources where there's a bunch of big files that come down first and then smaller ones and then bigger ones and then smaller ones, okay? So the fingerprint of CF Montreal's article is basically unique. There's not going to be another Wikipedia article probably that has that same fingerprint. And if I'm using some advanced, I don't know, machine learning or something like that, I don't have to, like, even if a couple images are cached or things like that, as long as I get the general form of what that fingerprint is. Yeah, exactly. So the adversary will go ahead and so the adversary will go and they have to fingerprint the website first. So they'll cache everything, they'll look at it themselves, right? And you as a user, if you could cache the website first, then you wouldn't be vulnerable to this analysis, but you would have had to get it first somehow, right? So like, as long as the adversary gets you on the first time that you go to the website when you cache everything, then it doesn't help. So, so does this fingerprinting work? Is this in theory sounds like I can tell what Wikipedia article you're looking at, even though your traffic is completely encrypted. That's what it sounds like, okay? Does it actually work? Does it work in practice, like between a real computer and a real website? And so the answer is that, yeah, it basically does work. So here's one paper, and this is quite old, so they weren't using like crazy advanced algorithms, but they found that our attack identifies individual pages within the same website with 90% accuracy. And so they looked at a bunch of healthcare websites, they looked at banking information, they looked at legal services, and they looked at YouTube and Netflix. So they could tell what YouTube video you're watching just based on packet sizes going back and forth and that type of thing. Okay, so that's pretty bad, right? That's pretty bad for, I mean, this secure, you're on a website, there's a lock, it's supposed to be secure, all your data is supposed to be confidential, and yet I can just look at it, and through everything that the protocol is telling me, I'm not breaking anything. I'm just looking. I'm looking at what it's telling me to look at, and I can already tell what Wikipedia article it is. Okay? So the truth is, it is actually a really bad attack. But maybe I don't have this as a point. The one benefit, or the one like sort of silver lining of this attack is this attack does require the adversary first to go to the website and fingerprint all the individual pages so that they do a pattern matching. So they know what all the Wikipedia articles look like. Then when you go to it, they're going to match it against what they've seen. Okay? So by definition, this attack only works on websites that anyone can access. So a Wikipedia article, the adversary can access it, you can access on it. So that's the type of website that could be attacked. Does this attack work on your inbox for Gmail? It doesn't. Why?
Because not everyone can access.
Okay, can the adversary access it? No, so they can't go there ahead of time, fingerprint it, and then when you go to your inbox, they're like, oh, that matches our fingerprint. Okay? So it only works on websites that they can fingerprint ahead of time, and that by definition are public websites that everyone can view. Okay? So you still often want privacy from, you don't want people to know what public websites you're going to, right? But most of the things that you care about are the private websites where it's your account, your information, your messages, your stuff. And this attack just doesn't do anything on that, okay? At most, I mean, the adversary knows, oh, you're on Facebook, right? But then that's it. They can't tell anything, even if they look at all the packet lengths and things like that. They can't tell like who your friends are, what your images are, and things like that. Okay. Oh yeah. Sorry. I guess this is the last point. So fingerprinting only works on public websites that they can train or fingerprint ahead of time. Okay, now let's go back to that idea of mixed content. So let's say that you're weaving together 100 and some resources on a particular website. Some of them come over HTTP. Say the root page, like the index.html. So the root page, the page that loads everything else on the page, that we really want to come down over HTTPS because if we don't get that securely, it's going to load, it's going to choose all the other things that we're going to load. Okay, so we're going to end up loading a bunch of adversarially chosen stuff if we don't have protection on it. But what if like some of these flags, like in Wikipedia's case, it's very clean, everything comes down over a secure channel. But like, let's say that this US flag did not come down encrypted. Does that matter? Okay, so not much. No one wants to say, no, it doesn't matter at all. What's the most that the adversary could do? Okay, so they could replace that image with a different image. Okay, otherwise they couldn't really change anything else about the website. Okay, now you guys all work for Safari or Chrome or your favorite browser. And this is a website that Wikipedia did, and these flags are not protected. And in theory, an adversary in the middle could replace the flag images with other images. Your job is to say, should I tell the user that this is secure by showing a lock? Or should I say it's not secure because at least some of the stuff on the website is not secure? So what do you do? Who votes for showing the lock? Okay, or there's a third option, so we could try and warn the user. Is that what you mean by alert? Yeah, okay. So we could throw a fit and say, oh, this website, it's mixing content. And so that would be another. Who likes the lock? Who would absolutely not put a lock? Who would throw a fit and throw some sort of error message? Who's going to lose 20% on their grade because they didn't answer any of the questions? Just kidding. Okay, so yeah, and so it's up to the browsers themselves. So what the browsers do, there's no right or wrong decision. This is a policy decision. The first thing that they recognize is that some kind of things that come down are a lot more dangerous than others. So that little image, I chose that deliberately because it's not that consequential. okay? Let's say it's a JavaScript file that's coming down. And so the user is going to pull it down, and then they're going to start running whatever's encoded in that in their browser, right? Yeah, if that's not secure, then that JavaScript can do anything. It can rewrite the whole website. It can pull its own resources in. It can basically, mess around with the whole website, okay? So that's a lot more dangerous than pulling down a little image of a flag, okay? So what the browser did is they said, well, actually, they kind of changed their policy over the years. So I forget what my slides say exactly, but we'll see. Initially, they actually did the alert thing. So they would show you, sometimes they'd show you a lock with a cross through it. And then if you clicked on it, it would say, warning, this website is sort of mixing content. Sometimes they would, then basically where we end up today is they split resources into what they call active and passive resources. So active is like any kind of scripting. Passive would be something you just display to the user like a picture. And so if it's passive and it comes down not secure, they say, we don't care, we'll show the lock anyway. If it's active and it comes down, they're not going to show the lock. And in fact, what they're going to do now is they're going to block it completely. They're going to say, you don't even download that, we're going to throw it in the garbage. And actually now what they'll do is they'll try and re-render the rest of the page with that file missing. And then probably the website's going to break. But they might show you the lock anyway because everything that they didn't throw away was served over HTTP. Okay, so passive content would be things like images, audio, video, objects. And then active content would be scripting, links, iframes, JavaScript initiated requests for websites, any kind of scripting things like fetches. And then objects are sort of, I won't go into those details, but whether they're active or passive depends slightly. So this is for Firefox. Different browsers do it differently. And so if there's no mixed content, then they'll show you the lock. If there is content that's mixed and it's active, so you're getting at least one JavaScript file that's not over HTTPS, then they'll display a lock with a line through it. And they also, I believe, will just block. If it's JavaScript, they'll block it in addition to that. I don't think it says that here. And then if there's like images and things like that coming down, then they have a slightly different warning. So they have a lock with a gray like kind of warning sign itself. Okay? So now as users, you're using this website. Do you know what the difference of that is? You might not even notice, right? Like you're on a website and you get this padlock instead of this padlock, you might not even notice it, kind of thing, okay? So you can think about the usability consequences of this. That's something we're going to circle back to in a bit. Next class. This is a nice website if you want to try out what some of these errors look like on your browser of choice. It's called the website's called badssl.com. And then it has a bunch of different bad websites that it will serve to your browser. And so there's a bunch of different errors that are baked into it. And by the end of the next 3 lectures, you'll understand what a lot of these things mean. But in terms of mixed content, let me find it. So this is a mixed script website. And so you can see in Safari, it does show the lock. And I think what happened in Safari, in fact, I know it because it's on the slide, is what Safari did is it actually deleted the bad script that it tried to download. So this website tried to download a JavaScript. It saw that it wasn't coming over a secure connection, and it just deleted it. It didn't load it. It threw an error. The error can be seen somewhere, maybe here. Yeah, so the page at mixedscript.badssl was not allowed to run insecure content from non-secure.javascript. So it tried to download it. It noticed that it did not come over a secure connection. It said, I'm not going to run it. And then Because the rest of the website, once you throw away that thing, the rest of the website is over a secure content. It's showing me the lock anyway, because what's left on the website is secure. And then they have a second one that's like a very bad version. And so here they don't show the lock at all. If I go into inspect element, I can see the errors. I have it on the slide, so I'll just read it from the slide. There's also a form where, like, sometimes when you submit information to a website, in this case, the website might come down over HTTPS, but imagine when you send it back, you try and send it back over HTTP, then generally you're going to get a warning. You've probably seen this warning before. You probably clicked through it. You might not have thought about what it means, but now that we're looking at this topic, this is what this means. This is a non-secure form. What that means is that this submit button is wired to a link. So there's a link that's in the HTML of this website, and it says whatever the user types into this box, pack it up and send it to this address. And the address that they chose is not over HTTPS. So they chose to send it to an HTTP address. And so your browser will always warn you about that. And why does it warn you? Well, anyone that's in the middle can read what you're being sent. And what are the kinds of things that you tend to type into these boxes? You know, usernames, passwords, credit card numbers, that type of thing. So they're highly likely to be sensitive. And so that's why the browser kind of goes crazy when they see you trying to send any information in a non-encrypted way. Okay, so this website, if we go into inspect element, these are the errors that it would show. So they allowed them to display an image that was insecure. It warns you, but you don't see it unless if you're a developer looking at it. It notifies you that this form, if anyone actually submits something over the form, they're going to get warned. And then it blocks this JavaScript from running on the website. And all of this adds up to enough bad stuff that they decide that they're not going to show the lock. Okay, so anyway, the moral of the story is it's sort of, it's a mixed bag. Browsers do it differently. The policies differ slightly. The user interfaces differ slightly. What they show you differs slightly. But more or less, no browser is going to let you download arbitrary JavaScript and run it if it didn't come over HTTPS. Okay? And if you're just downloading an image, it's probably going to be okay. No browser is probably going to complain in a way that's visible to the average user about some picture that you downloaded over a not secure connection. Okay? And then everything else that's sort of in between, it will vary slightly based on the browser itself. Okay, so this is good. This is sort of a dead end in our attack tree. Because my idea with the attack tree was, well, if I could get malicious JavaScript into the website, then I could kind of take it over, and then I could learn what the content was that was being sent. Or if I could get that form to post HTTP instead of HTTPS, then I could read the content that's being passed over the form itself. Okay, another attack that we might think about is if we can only see encrypted data, we assume that HTTPS is perfect. We don't have any way of breaking the tunnel. Is just because we can't break it today, does that mean we'll never be able to break it? Okay. And so the history of HTTPS actually tells us that, you know, data, if you were around when people were using SSL 2.0 and they were using an algorithm called triple des, and you actually wrote down everything that people were saying, you couldn't have broke it at the time that you wrote it down, but if you stored it and today you took a look at it, you could break that data. Okay? And so now, you know, especially big governments, you know, intelligence agencies and things like that, they've woken up to this idea. We can't break it today, but we don't know what the future holds, right? We think there's these quantum computers that are coming, you know, in 20 years, and those we hear that those things can break crypto. Right? So what if we just store everything today? Now, obviously, a lot of the data is not useful from an intelligence perspective if it's 20 years old, but there's definitely stuff that's still relevant in 20 years. Okay? Geopolitical things or things that people said, like military leaders and things like that. Okay? So anyway, I'm not telling you that the NSA is storing all of internet connection, like all internet communications that it can get its hands on in a big purpose-built data center in Utah, but it's possible, and they do have a big data center in Utah, and if you look at the satellite pictures, it looks like it's for exactly that purpose, but of course no one knows because it would be classified. Can we do anything about that? So the answer is yes. So we, again, I'm not going to go into the details, but there are different ways of setting up the crypto. So there's a way that you can set up the crypto that if somebody can break it in 20 years, they can decrypt it and learn all of it. And there's other ways of setting up the crypto so that in 20 years, if people break it in certain ways, then even though that they can break it in certain ways, it doesn't let them actually recover the data. Okay? Now, I'm being very careful about what I say, and it sounds like very well qualified because these crypto attacks are kind of, they're kind of subtle. But anyways, HTTPS has moved to the sort of the better form of encryption now. It used to be a choice. So between you and the website, you would choose what kind of encryption you wanted to use, and you may use future-proof encryption or you might not. Okay? But now, you, by default, if you have the latest version of TLS and the server supports it, there are no options that are not this, okay? They all have this perfect forward secrecy. Now, there is still this thing called a session key, and the session key is encrypting your data. And if I'm able to get that session key, or if I'm able to decrypt the data without the session keys because of some flaw in the encryption algorithm, then I can still read this information. Okay, so there are still reasons for the NSA to collect this information anyways, but specifically the kinds of algorithms that quantum computing is good at solving, it's good at solving certain kinds of crypto algorithms that are not this. Okay, so once you use this kind of thing, you're, at the end of the day, the only thing that's left to break is a quantum computer is not going to help you break it. Okay, there is something there for people in 20 years to break, and if they break it, they can read data, but a quantum computer is not going to help them. Okay, it will help them break it will basically help them break where the tunnel ends up pointing. That's the property of HTTPS that will break with a quantum computer, but not the actual confidentiality. Okay, so anyways, I know that's like kind of vague and it doesn't make a lot of sense until you take crypto, but anyways, I'm not going to test you on the finer details of this kind of thing. Okay, so what we can do is we can sort of toss this into the attack tree. So this is the sub part of the tree where we're recovering partial data from external observation. And so first off, the first thing we can do is we can learn everything that doesn't go over HTTPS. Okay, there's a bunch of stuff that's on the outside of the envelope, and that's pretty good. Okay, so like, you know, based on the header is a fancy way of saying the outside of the envelope. We know what domain is being visited. If we see the DNS query, we also know what domain is being visited. And any content that gets mixed into the website that's not served over HTTPS, we could also see. Okay, so we can see those flags or those images or things like that. All right. We could also try to modify the content that doesn't go over HTTPS. And so if we could get JavaScript, we see you trying to pull down JavaScript, then we modify it. Then we could run the JavaScript and have the JavaScript ask the browser, what's everything else that's on this website? I can't see it. And then pack it up and send it off to a server of our choice. So JavaScript is very powerful, and that's like something that it could totally do. But luckily for us, this attack basically doesn't work because browsers won't let us get HTTP loaded JavaScript. Now, if we could modify the JavaScript some other way, like say it's a common library, everyone uses it, lots of websites use it, it's sitting on GitHub, and I somehow get access to that repository and I change it on the repository, now everyone downloads it and they have my malicious stuff mixed in, then I can do this attack. That's not an attack on HTTPS, that's an attack on JavaScript and how browsers use JavaScript and how dependent everything is on scripting. And we will see that attack at the end of the course where it's called cross-site scripting. And so anyways, we'll revisit that attack, but that's just a teaser for that. Yeah, and then I can look at like how many packets, how big are they, the order that they're going through. If I can fingerprint public websites first, I can try and match the patterns that I'm seeing to what I see on the public web, and then I can figure out what websites you're going to, even though you're going to them over HTTPS. And then if I'm some sort of like country or nation state, then I could do something like store all internet traffic and get it all routed through me, make a record of it, and then I'll keep it for later and then try and break it in 20 years. Okay. So questions about that external? Okay, so then we'll jump into breaking the tunnel inside. And this I'm going to say very little about because it requires a lot of crypto. And I'm not going to assume that you have crypto. But I do want to give you the flavor of the attacks, and I want you to see, one thing is to see how complicated they are. These aren't simple attacks. I want you to sort of appreciate the fact that you have to chain together a bunch of different things in order to make them work. So we'll look at one in sort of a kind of a high level, but I'll try and walk you through the main components of the attack. Okay, so what is the tunnel? When we talk about the tunnel, right, it's a bunch of crypto that's happening between two parties, okay? And these two parties have keys. So a key is a random number, like a password, it's just longer and machine generated. And whoever has the key has access to the tunnel, and if you don't have access to the key, then you don't have access to the tunnel, more or less, okay? That's the level that we can understand, okay? So as a goal to get into the tunnel, one way we can get into the tunnel is to get the key. If we can get the key, we can get into the tunnel. The other way is we could try to break into the tunnel without the key. Okay? Maybe possible, maybe not. You would think if the crypto works perfectly, it probably isn't possible. But we will consider whether HTTPS's encryption does work perfectly, or has it always worked perfectly. And so we'll consider those attacks as well. Okay, so we can either steal the key or we can break the protocol without using the key. Okay, so one way to before talking about HTTPS specifically, let's just take a pause and talk about something completely different. One way of attacking systems in general is called side channel analysis. So side channel analysis is basically, when I design a system, I assume you're going to attack me a certain way. So if it's a crypto system, I'm assuming that you're going to try and break the key, or you're going to try and look at the packets and try and decrypt them and things like that, okay? And everything I'm not assuming about like how you might attack my system, we consider it a side channel, okay? It's something that basically wasn't taken into consideration by the designer of the system, and it's usually like super weird things, okay? So one example would be, let's say I'm decrypting messages. You send me a message, I decrypt it. You send me a message, I decrypt it. You could look at how long does it take me exactly, precisely to decrypt something. Okay, you see the message come in, and after I decrypt it, maybe I do some action. And so you can measure the difference in time. And if you're controlling the messages that I'm decrypting, you could send me one kind of message and see, oh, that I'm really quick to decrypt that message. And then you send me a different message, and that takes me a bit longer. And then you could look at the encryption algorithm and say, I wonder if that tells me anything about the key that's being used, right? That these kinds of messages take longer to decrypt than these other kinds of messages, okay? And so whether that works or not is going to depend a lot on the mathematics of the crypto that's being used. So some crypto algorithms, for example, RSA, some of the attacks are on RSA itself. Sometimes it's when you pad out RSA with some extra stuff. But basically, you can use time, and you can look at how long it takes for things to get decrypted, and you can back out what the key needs to be in order to see that timing pattern that you're looking at. Now, these are usually done in a lab setting, so they have really good, fast, measurements, and they're sending like 10 million packets to get like 10 million samples of time before they can sort of chart it and figure out what the key is. And if you tried to do this in real life on a real computer, you would probably get cut off because of the amount of network traffic that you're generating or things like that. So these are kind of theoretical attacks. But in theory, in a lab, you could read the decryption key of an RSA key off a computer if you could measure how long it takes to decrypt arbitrary ciphertext that you choose. Okay, so we call that a side channel. Side channels show up a lot in security, not just in crypto. So some examples are early ATMs. If you could measure the power that it was drawing the hydro very sensitively, when people typed in their pins, when you press the number 1, it would create some resistance, but it would be slightly different than if you press the number 2 or the number 3. So if you're sort of watching someone, you can't see the pin that they're typing in, but you can see that they are typing in their pin, then you can look at the power graph and you can just sort of read their pin out. Very similar, there were some voting machines. This was in the Netherlands, it probably worked elsewhere. Same idea, there was different buttons to vote for different candidates. Each button created a bit of electromagnetic interference, and it was slightly different depending on the button, right? So someone literally stood outside, they weren't even in the room, they were outside the building, they had a radio, very sensitive radio, but it was like something you could buy. And they were there and they could tell how people were voting, or more precisely, they could tell which buttons people were pressing based on the signals that they were getting from this radio. There's an example of sound. So like a lot of computers make, especially when I was growing up, they were a lot noisier than they are now, but they make these like weird clicking sounds and like kind of staticky like kind of sounds. And it's like stuff that's going on in the computer. I don't know the full explanation for it. But one cryptographer, actually the S in RSA, Adi Shamir, he had one of these old computers and he got curious about it and he said, I wonder if I measure like that sound, if I record it very sensitively and I record it while I'm asking it to do RSA decryptions, if I could do kind of similar to this, if I could actually read out the key. And so it turned out he tried it and it turned out he could. He could figure out like what, based on like the sounds it was making, it's doing a memory here or it's doing some expensive operation. I forget the exact origins of it, but you could reverse out what the key was. Gyroscope. So most phones have a gyroscope. Why? So if I turn my screen like this, it figures out that I'm looking like this. Augmented reality, like all these kinds of things. As I'm typing, I'm like rocking my phone slightly, right? Or if I type over on the, if I type on the far side of the phone, I'm pushing it down a lot. If I type more in the middle, it's like a little more solid, okay? If you take really fine gyroscope measurements, you can figure out what people are typing on the keyboards because every tap pattern is slightly different depending on where they're tapping on their phone. Often here you have to train first. So you'd have to get the user to type out some stuff and know what it is and train on it. Then you could recognize it later, but that's another side channel. Reflections, so I'm looking at my computer here. You already know what I'm looking at, but I'm wearing glasses. With a sensitive camera, you could, even from a building, say it's two like big skyscrapers side by side, someone with a very sensitive camera could look into my glasses. It's going to be all distorted, but you can do the correct optical operations, have a computer do it, and reverse out like what I'm looking at on my screen. So anyways, the sky's the limit, but this is this idea of side channel analysis. So side channel analysis for time, and in particular with crypto, sometimes there's like, I mentioned that if something gets modified in the middle, you can detect it. And if it gets detected, then the server is going to respond in a certain way than if there was no modification that was detected. And so often what you're doing is you're modifying things and then you're seeing whether they're catching the error or not. And that's telling you some information about the keys that they're using. So that's what this padding oracle is in very simple terms. And so these things are real. You can do them on HTTPS, at least in a lab setting, maybe not in the wild. Okay, here's another attack. Okay, so this is called Heartbleed. It happened a while ago, and this is a real life thing. It was an attack. It was like actually in the news. Like if you picked up, I don't know, the New York Times or CBC or like some real mainstream mainstream news source, they would have articles about Heartbleed when it happened. So it was sort of a big deal. Actually, you know what? I'm looking at the time. I think maybe it's better to save this one for next class because it takes a while to explain the whole thing. So we'll put a pin in it. We'll save it. But before we go, is there any other any questions about all the stuff up to but before Heartbleed itself. Okay, great. So enjoy your week, and I'll see you all next week.